how can we apply the goodness of fit tests or the goodness of fit procedures to discrete observations? So the other way that we apply the goodness of fit test to test this hypothesis for a continuous distribution cannot be applied for discrete distribution. Why? Because, the cumulative distribution function for the discrete random variables is stair-shaped, and it is not a one-to-one function, unfortunately. So we should directly apply a goodness of fit test for the discrete observations directly. I mean, we cannot use this approach for discrete observations. So how do we apply goodness of fit test for discrete variables? First of all, you cannot apply Kolmogorov-Smirnov test at all. Or you can apply it, but it is going to be a little tricky. So we are just going to assume we have enough observations for the discrete sample. And we are directly going to apply a chi-square test for this discrete sample. And the procedure is as follows. Because we have discrete observations, we are going to count the number of observations from each value j in the data, and we will call them the observed frequencies. So let's just say I have a discrete data which contains of only 5 different values, 1, 2, 3, 4, 5. And I'm just going to count the number of observations of 1 and the number of observations 2, 3, 4, so and so forth. And I'm just going to call them OJ, which is the observed frequencies of each observation. And obviously, the hypothesis that I have is going to give me a probability mass function. And with respect to this probability mass function, I am going to calculate the theoretical probabilities of j's. So I'm just going to calculate the theoretical pj values, which are the probability mass values at j, the probability of a random variable to be equal to j. Again, the observed frequencies are somehow the empirical fractions, and these pj values are the theoretical fractions. Then, for each value in the data, I am going to calculate the expected frequency. If pj is the probability of getting a j value in this theoretical distribution, then if I sample n observations from that distribution, then the number of observations that we expect is n times pj. So in n times pj of the observations, we expect to observe j. This is the expected observation. Now you see, if my hypothesis is really true, if this sample really follows that distribution, then these oj and aj values must be very close to each other. And there is one more golden rule, my friends. If the expected frequency, expected number of observations is less than 5 in any of the values, then I need to combine this class with the closest class, because otherwise I cannot have a chi-square test statistics. If I want to have the chi-square assumption, then the expected frequency in any class should be greater than or equal to 5. Then the next step is this. Again, just like in the chi-square test statistic in the uniformity test, again, I'm going to calculate the chi-square test statistic. I'm just going to find the difference between the observed frequencies and the expected frequencies in each j value. And the differences will be divided to the expected frequency in that class. And for all of the classes, I calculate the summation. I'm going to sum this over the classes. And then I'm going to compare this test statistic with the critical value that I obtained from the percentage points of the chi-square distribution. However, the degrees of freedom here must be what? Remember, in the uniformity test, we were determining the degrees of freedom as number of classes minus 1. So number of subintervals minus 1. However, there is an S here. This time there is an S here. What is this S? The number of parameters of that distribution, right? So for every parameter that we have estimated in the null hypothesis here, we need to subtract this number of parameters to determine the degrees of freedom. So if the test statistic, my friends, is greater than the critical value, then we reject the null hypothesis and we say that the sample does not follow that discrete distribution with that parameter setting. However, if the test statistic is less than or equal to the critical value, then we should say that there is not enough evidence to say that the sample does not follow that distribution. The sample may as well come from that discrete distribution. So I'm just going to solve a question based on that. So let's read the question. It says the number of vehicles arriving at the northwest corner of an intersection in a 5-minute period between 7 a.m. and 7:05 a.m. was monitored for 5 workdays over 20-week period. The following table shows the resulting data. Notice that the number of automobiles arriving to the intersection is a discrete variable. Therefore, the histogram may have a self for each possible value in the range of the data. So the table tells me that in these 100 days, in 12 of these 100 days, 0 cars have arrived in these 5 minutes. In 10 of the 100 days, only 1 car has arrived to that intersection. In 19 of these 100 days, 2 cars have arrived. So this is basically the number of observations. These are observed frequencies. So in 100 of observations, we have observed 0 12 times, 1 10 times, 2 19 times. Assuming independence among days, we want to fit a statistical model for the number of arrivals, and we check the histogram of the observed frequencies, we get a shape like this. And when we check this shape, which discrete distribution can fit to this histogram, one can say Poisson distribution can be a good fit. Let's see if it is going to fit or not. Now, remember, these are my observed frequencies. In 12 of the days, I observe 0. In 10 of the days, I observe only 1 car. In 19 of the days, I observe 2 cars, so on and so forth. Now, if I am going to check if the distribution follows Poisson distribution, I need to check the lambda parameter. And how do I check the lambda parameter? I have 12 zeros, 10 ones, 19 twos, 17 threes. I need to sum up all of the 100 observations. So I need to multiply 12 with 0. I need to multiply 10 with 1. I need to multiply 9 with 2 and write them here. And when I sum them up and divide it to the observations here, it will give me the average of 3.64. So the average number of cars arriving in these 100 days in that intersection is 3.64. Okay? So my hypothesis is this. My sample follows a Poisson distribution with rate parameter being 3.64. Now, if I want to perform my hypothesis test, first I need to calculate the theoretical probabilities under this parameter setting using the probability mass function of the Poisson distribution. And after calculating these probabilities, I am going to multiply these probabilities with 100 because my sample size is 100. So I am going to determine the expected frequencies coming from this theoretical distribution indicated in the null hypothesis. So my observed frequencies are here. The probability mass values calculated according to the Poisson distribution are here. When I multiply these values with 100, I get the expected frequencies. These are observed frequencies. Now, remember, there was a warning here. If the expected frequencies are less than 5, we need to combine that class with the closest class. Now, I need to combine the classes with the closest class if they have expected frequency less than 5, which means the first class here that belongs to 0 must be combined with the closest class, and the last class must be combined with the closest class. Even if it is combined with the closest class, still it is not greater than 5. So I need to combine it with the closest class again adaptively. So as you can see, the last 5 classes must be combined and the first class must be combined with the second class. Then you see we update the expected frequencies like that after combination, and the observed frequencies must be updated as well. So the observed frequency in the combined class will be 22, and the observed frequency in the last combined classes is going to be 70. So this is a necessary thing to do, my friends, until the expected frequencies are greater than or equal to 5. Now I am ready to calculate my test statistic. After the combination, I only have 7 different classes. For each of these 7 classes, I calculate the squared deviations between the observed frequencies and the expected frequencies, and they are normalized by dividing them to the expected frequencies. Then I sum up these values to get my chi-square test statistic, which is 27.47. How many classes do I have? I have 7 classes. I have a single parameter estimated from my sample, so I subtract it. And I also subtract another value, 1. Remember, my degrees of freedom is 5. So with degrees of freedom 5, I need to check the chi-square table. My degrees of freedom is 5, and you can see with 0.05 significance level, my test statistic is 11.1. So I need to compare 27.47 with 11.1. My test statistic is a lot greater than the critical value. So what is my conclusion? The sample does not follow this distribution, does not follow Poisson distribution. Even if I use the suggested estimator, it is not following it. This means if I choose another parameter, still the Poisson distribution will be rejected. There is enough statistical evidence here to reject the Poisson distribution. So what is the thing to do that? I mean, I see that the Poisson distribution does not work as a fitting distribution. I can either try to find another theoretical distribution and test if it follows that distribution or not, or I can simply use the empirical distribution. So there is nothing more to do here. I need to use the empirical distribution. I can simply calculate the probabilities according to these fractions, according to the observed frequencies here. I can proportionalize the probabilities, and I can generate my random variates from this proportionalized discrete distribution, which is called the empirical distribution.